Welcome back to The Explainer. Today we're exploring a mashup I honestly never thought we'd see. 3D graphics crashing headfirst into quantum computing. I know, we're talking about two massively complex fields here, but the way they're intersecting right now is going to completely rewrite how we create and experience virtual worlds. We're unpacking a groundbreaking paper from June 2026 that introduces a totally new, quantum mechanics-based way to render light and materials. So let's jump right in and see how this tech is pushing computer graphics past the uncanny valley and into true physical reality.
All right, here's our roadmap for today. First, the limits of traditional rendering. Second, a quantum shading framework. Third, decoding subsurface scattering. Fourth, quantum computers meet graphics. And finally, physics-inspired virtual materials. Starting off with Section 1, the limits of traditional rendering. Before we can really appreciate this quantum solution, we have to understand the classic roadblock graphics programmers have been wrestling with for decades. Traditionally, light rendering assumes that the optical properties of materials are just static. Basically, the math assumes a surface behaves the exact same way no matter what kind of light hits it. But in reality, that assumption totally breaks down. The paper points out that optical properties actually dynamically evolve in response to incident illumination. When complex light hits a complex material, the material's properties fundamentally change in real time. So by treating these properties as static, traditional rendering is literally missing out on an entire layer of physical reality. Which brings us to Section 2, a quantum shading framework.
This whole framework comes from a June 2026 paper titled Rendering Coherent Scattering via Quantum Collision Models, authored by João S. Ferreira, Spencer S. Topol, Pierre Fromholz, and James R. Wooten. And what makes this so incredibly cool is how cross-disciplinary it is. We are spanning graphics, popular physics, and quantum physics all at once. They aren't just tweaking some old graphics algorithm. They're ripping fundamental principles straight from quantum mechanics to completely rewrite how light interacts with virtual matter.
The authors lay out their missions super clearly, stating, "We present a novel shading framework that combines classical ray tracing with a quantum collision model to explore the effect of coherent light-matter interactions in rendering." Notice what they're doing there. They aren't throwing away classical ray tracing, which is the powerhouse behind today's high-end graphics. Instead, they're combining it with a quantum collision model. They are actually simulating the true physics of photons interacting with a material's atomic structure rather than just faking it with the usual surface-level math.
Let's move to Section 3, decoding subsurface scattering.
So how exactly is light being reimagined here? Well, the methodology breaks down into 3 core steps. Step 1, treat the incident light and material excitations as quantized modes. Step 2, model subsurface scattering as symmetry-constrained unitary collisions. And Step 3, incorporate chaotic optical responses. It sounds dense, I know, but let's break these down one by one to see what's actually happening under the hood.
Step 1 is absolutely crucial: quantized modes. Instead of treating light as just a continuous beam of color, the authors treat the incoming light, the incident illumination, as discrete quantum-level states. And they do the exact same thing to the material's internal reactions, or excitations. By mathematically quantizing both the light and the matter, they're finally speaking the true language of physics. They're setting up a system where these two elements can interact dynamically, exactly like they do in the physical world.
Next up, we have unitary collisions. Now, trying to calculate the actual quantum collisions of light bouncing around inside a piece of jade sounds like a surefire way to set your graphics card on fire, right? But in physics terms, they're tracking a sequence of symmetry-constrained interactions to model subsurface scattering. See, when light hits a complex material, it doesn't just bounce right off. It penetrates, it scatters around inside, and then it exits. Traditional math just sort of blurs things to fake this effect. But this new model, it replaces those old approximations with a sequence of genuine quantum interactions tracking the light as it physically collides within the material's internal structure.
And tracking those actual collisions leads us to this massive breakthrough. As they put it, this formulation allows for the incorporation of non-integratable dynamics and chaotic optical responses due to multi-layer interference effects. This is a real game changer. Because they're calculating actual quantum collisions beneath the surface, they unlock incredibly complex, chaotic light behavior. When light hits multiple layers inside a material, it literally interferes with itself. It creates chaotic optical responses that dynamically evolve. Rendering this level of physical reality was straight up impossible with those old static assumptions we talked about earlier.
All right, Section 4, quantum computers meet graphics.
Now, as you might guess, calculating quantum collisions, non-integrable dynamics, and multi-layer interference requires a monstrous amount of computing power. You absolutely cannot run this in real time on a standard consumer graphics card. So to handle that heavy lifting without destroying standard hardware, the researchers propose using near-term quantum computers to pre-compute these complex collision operators. By offloading the hardest quantum math to actual quantum hardware ahead of time, they perfectly bridge the gap between theoretical physics and practical rendering.
And that leads to a purely brilliant piece of practical engineering, packaging all this data into standard BSDFs. Now, a BSDF is essentially a standard file format that tells a graphics engine how light should scatter off a given surface. The sheer genius of Ferreira and his team is that despite all this mind-bending quantum math and heavy pre-computation, the final output gets wrapped up perfectly into standard BSDFs. That means your regular graphics software and current classical ray tracing engines can just read and use the data without missing a beat. They've effectively smuggled quantum complexity inside a standard wrapper that the graphics industry already uses every single day.
Finally, Section 5, Physics-Inspired Virtual Materials. So what is the ultimate takeaway here for creators and gamers? First off, it means the rendering of entirely new physics-inspired materials. Because we're no longer handcuffed by static approximations, artists can create virtual materials that react to light exactly as they would in real life. Second, these materials are going to exhibit completely distinct optical signatures. Since that chaotic multi-layer interference is genuinely being simulated, materials will look hyper-realistic, dynamically evolving based on their specific environment. And third, we finally get a true representation of coherent light-matter interactions. It's an unprecedented level of physical accuracy for computer graphics.
Think about it. If we can use near-term quantum computers right now to pre-compute and render entirely new physics-inspired materials with dynamically evolving chaotic optical signatures, what will the virtual world of the future actually look like? Once our rendering engines stop faking light and start simulating actual physical reality, that line between digital and physical is going to completely vanish. Thanks for joining me for this explainer. Keep your eyes on this space, because for sure, the future of graphics is quantum.